Hi everyone, welcome to lecture 26 of your electric circuits class. And lecture 26 is about impedance, KVL, and KCL. So the objectives of this lecture, the first one, that define impedance, and obtain the equivalent impedance of a given circuit. And the second objective is to use KVL and KCL to determine voltages and currents in AC circuits. So we will start with impedance here. So impedance, we can define it as the property of a circuit element in opposing the flow of current in AC circuits. And the impedance is measured in ohm. The symbol of it, so it is denoted by the uppercase Z, and we will put tilde, while in your textbook it will show like a bold letter because it is a phasor. So by Ohm's law, for AC circuits, we can say that the impedance, which is phasor Z, is equal to phasor V divided by phasor I. So all of these are phasor quantities, they are complex numbers, and that is equal to Vm with angle theta V divided by Im with angle theta I. So if you look at this here, since theta I is in the denominator, when we bring it up to the numerator, we will flip the sign. So that will be Vm divided by Im, and the angle here is theta V minus theta I. And that is as what we said in ohm. So what about impedances of circuit elements? So impedances of circuit elements. We have circuit element here and impedance here. So for resistance, which is R, the impedance of R is equal to the R value. And then for the circuit element, which is inductance, our impedance is equal to J omega L, which is equal to J 2 pi FL. And for C, which is the capacitor, the impedance of a capacitance, that is 1 over J omega C, which is equal to 1 over J 2 pi FC. And now if we want to bring that J from the denominator to the numerator, we have to flip the sign of that J. So that will be negative J over omega C, and that is negative J over 2 pi FC. So now, since our impedance is a phasor quantity, which is a complex number, it can be represented as R plus or minus Jx. So the R here is the real part of Z, and the X is the imaginary part of phasor Z. So now, why we have over here a plus and minus? It depends on the impedance. So for inductive impedance, we will have our Z is equal to R plus Jx sub L in rectangular form. So R is the real part and XL is the imaginary part, which means that in polar form, that will be the magnitude Z with angle positive theta, because this over here is positive, so this over here is positive. And for capacitive impedance, we will have our Z is equal to R minus J X sub C. And in polar form, phasor Z will be the magnitude Z with angle negative theta. So now when we are saying that inductive impedance, the inductive impedance look like this. A resistance connected with an inductance. And for capacitive impedance, we have our R connected with a capacitance. So that is R minus J X sub C. And of course that we can have our impedance triangle. So our R at the base here, our X is here if it is XL, and over here we have Z. So over here, and that is our angle theta. So this over here, inductive impedance. For capacitive impedance, it will look like this. So this is our theta, which means it will be negative. And over here we will have X sub C. This is our R, and this is the magnitude of the impedance. So this here we can say capacitive impedance. capacitive impedance. And of course, in both cases, we can say that the magnitude Z based on the impedance triangle, that is equal to the square root of R squared plus the reactance squared, and our R is equal to the magnitude Z cosine theta, and our X, which is the reactance, that is Z sine theta, and the theta itself, that is the inverse tangent of X over R, so reactance divided by resistance. So impedances in series it is the same as when we find our equivalent resistance. So we can say that the total or equivalent impedance for n impedances connected in series will be the total. So Z total is equal to Z equivalent, and that is equal to Z1 plus Z2, and all of these are phasor quantities. Z3, it depends how many impedances in that series combination. And impedances in parallel, the total or equivalent impedance for n impedances connected in parallel 1 over ZT, which is 1 over Z equivalent, that is equal to 1 over Z1 plus 1 over Z2 plus 1 over Z3. It depends on how many impedances that we have in that parallel, let's say, combination. However, that for two impedances in parallel, it will be easier to use this formula here. You just multiply Z1 by Z2 and you divide by their summation, Z1 plus Z2. Please don't forget that all of these are phasor quantities, which means that complex numbers. So let us go over an example to show you how we can determine a total or equivalent impedance. So we would like to find the equivalent impedance of the shown circuit if the operating frequency is 60 Hertz. And this is our circuit here. We need to find Z equivalent here. This is 6 ohm, 100 microfarad. There is another capacitor here which is 50 microfarad. This is a 3 millihenry. That is 6 ohm, and this is 2 millihenry. So when we need to do our solution, first you have to make sure that the circuit is given in phasor domain. What we mean by that in phasor domain, all elements are given in ohm. So if we look at our circuit here, we have 100 microfarad, 2 millihenry, 3 millihenry, 50 microfarad. And of course that this here, the resistance is given in ohm. That is in ohm. So now if you look at that, these are not given in ohm. So we have to convert those to be in phasor domain, which means that the 100 microfarad, we have to find the reactance of that, or the impedance of it. Same thing that with for the 3 millihenry, 50 microfarad, and 2 millihenry. The way to do that, we can say, okay, we will start with the Z of the 100 microfarad. And that is equal to 1 over J 2 pi Fc. And that is equal to 1 over J 2 pi, and the frequency is 60, and our C is 100 micro, which is 100 to negative 6. And that is equal to, now look at this, I have the J in the denominator, I have to bring it to the numerator, then it will become negative J. So that is negative J. And then I will divide 1 by 2 pi 60 times 100 times 10 to negative 6. That will end up with 26.53. And now that is given in ohm. The second one is the Z of the 50 microfarad, and that is 1 over J 2 pi Fc, and that is equal to 1 over J 2 pi times the frequency, which is 60, times the capacitance value, which is 50 micro, that is negative 6. And then we will end up with negative J 53.05 ohm. Then we need to find the impedance of the 3 millihenry, and that is omega L, right, which is 2 pi FL, and that is 2 pi times 60 times the value of L, which is 3 times 10 to negative 3. Then we will end up with a positive J 1.13 ohm. Then the Z of the 2 millihenry, and that is 2 pi FL, which is 2 pi times 60 times 2 times 10 to negative 3. And the answer here for 2 millihenry, that will be J 0.754 ohm. So from that, we can get our circuit as this. This is 6 ohm, and then minus J 26.53 ohm, this is J 0.754 ohm, negative J 53.05 ohm. This is 6 ohm, and this is J 1.13 ohm. And this is where we need to find our Z equivalent. So now this is phasor domain representation. So now our circuit in phasor domain, everything, all the elements are in ohm. Then we can find our, let's say, equivalent impedance. So in this case, if you look, we have said that when you want to find your equivalent resistance or equivalent, let's say, impedance, just start from the farthest point from the terminal. So that means we are going to start with these two elements here. So 6 ohm parallel with, 6 ohm is in series with J 1.13. And then 6 plus J 1.13 are in parallel with negative J 53.05. So for this case here, that is equal to 6 plus J 1.13 times negative J 53.05 divided by the summation 6 plus J 1.13 plus negative J 53.05. So you are doing exactly the same as what we are doing in the equivalent resistance when we have parallel resistors. However, you are dealing with complex numbers. And in this case, when you do this multiplication, you are going to get 60 minus J318 divided by 6 minus J51.92. And now when you do this division, you will get 6.182 plus J 0.44 ohm. So now we have done this part of the circuit. Then the whole thing is presented by this element here. Then that means the rest are all in series. Then we can say this will give us that 6 minus J 26.53. We just added them together because they are in series, plus 6.182 plus J 0.44 plus J 0.754. All of those are in series. So that will be 12.18 minus J 25.33 ohm. And this is our Z equivalent. So we have a term called admittance or admittance. So we can say that admittance is the inverse of impedance. So that means Y is equal to 1 over Z. And this is equal to G plus JB. This G here, we call it conductance, and this B over here, we call it susceptance. And of course that the unit for admittance, that is Siemens or mho, because it is the inverse of the impedance. It is the same as when we said that the conductance is the inverse of resistance. So we are inverting, let's say, the ohm. We are going the other way around, then we can call the unit mho. And usually that we give it, let's say, upside down of ohm. So that is mho. Regarding KVL in AC circuits, it is the same as the KVL in DC circuits. So over here we can say that KVL states that the summation of all voltages around any closed loop is equal to 0. That means summation of V's is equal to 0. That is KVL. And KCL in AC circuits the same as in DC. KCL states that the summation of all currents at any node is equal to 0. What that means? It means that summation of phasor I at any given node is equal to 0. Or we can say that summation of current in is equal to summation of current out. So let us take an example here. We would like to find VL of t and I of t in the shown circuit. And this is our circuit here. This is, let's say, our Vs of t is equal to 5 cosine 8t. This is the current I, that is 4 ohm. This is 0.3 Henry, and this over here is VL. So we need to find the current I and the voltage across the inductor VL. So when we have these values in italic, when we are saying that symbols of voltages and currents are given in italic format, That means we are talking about time domain. Time domain. So first of all, we have to have our circuit in phasor domain. So have the circuit in time domain. In phasor domain. In phasor domain. To do that, our Vs of t, that should be our Vs, which is equal to 5 with angle 0 volts. So we took this 5 because that is Vm, and there is no any associated angle. That means the angle is 0. Okay, and then we have our 0.3 Henry. We need to get our ZL in this case, and that is equal to J omega L, and that is J, and our omega is here, which is 8, because all the time the general format of a voltage is Vm cosine omega t. So omega is 8, and our L is 0.3, so that will be J 2.4 ohm. So now if you look at our circuit here, it is a single loop circuit. The total voltage, which is the source voltage, is given. Then we can use voltage division, let's say, to find our voltage across the inductor. So if we use voltage division, we can get our VL is equal to J 2.4 divided by the total impedance, that is 4 plus J 2.4, multiplied by the input voltage, which is Vs, and that is 5 with angle 0. And this over here, when we do it, it will be 1.3235 plus J 2.206. So this is here in rectangular form. To get that in polar form, we will just convert to polar form, and that is 2.573 with angle 59.04 degrees, and that is in volts. So we still have our quantities in phasor domain. Now the current I is equal to Vs divided by the total impedance, 4 plus J 2.4, and that is equal to 5 with angle 0 divided by 4 plus J 2.4, and the answer here is 0.9191 minus J 0.5515, and that is in rectangular form. We just convert it to polar form, and that will be 1.0719 with an angle of negative 30.96 ampere. So now the question is telling us to find this quantity and this quantity, and if you look at those, these are in time domain based on our explanation here, right? That is needed in time domain. So to do that, we are gonna look at our VL. So our VL came out to be this value, right? So we can say VL of t is equal to, if you remember, that is Vm cosine omega t plus theta v, right? That is the general form. So Vm is this value here, which is 2.573 cosine omega was given, which is 8t plus 59.04, and that is in volts. So this is our VL of t. So now our I of t, it is Im cosine of omega t plus theta I. That is the general form. Im is this value here, so 1.0719, and then cosine omega was given 8, multiplied by t, and then our angle, which is theta I, is this angle here, which is minus 30.96 degrees, and that is in ampere. So this is our answer for our current in time domain. By this, our lecture for today is done. So for this lecture, as long as you know impedance, admittance, series, parallel, and series parallel impedances to find total impedance, and you know how to use, let's say, ohms, KVL, and KCL to solve for voltages and currents. You will be in good shape. And our homework for this lecture is here, 2 problems. And thank you for watching.